Flat bottom hull. The flat bottom hull is the oldest engineered boat shape in existence, unchanged since ancient Egyptians used reed vessels on the Nile. Its bottom is perfectly horizontal, producing a dead rise angle of 0 degrees. At rest and at low speed, no hull shape offers more initial stability at equivalent width, making it the standard tool for shallow water anglers, duck hunters, and river navigators. A flat bottom skiff can operate in as little as 3 inches of water. The limitation appears the moment the water stops being flat. The hull has no pointed entry and no keel, so it wanders in crosswinds and pounds violently in chop, with the entire underside contacting each wave simultaneously. It dominates calm inland water because it is inexpensive to build, simple to maintain, and extraordinarily capable in the environment it was designed for. Deep V hull. The Deep V hull was developed in the late 1950s by American designer Ray Hunt to solve a specific problem. Existing hull shapes could not handle open ocean at high speed without punishing their crews. Hunt extended the V angle sharply from bow to stern, producing a transom dead rise of between 18 and 25 degrees. As the hull moves forward, the sharp V entry divides each wave and forces water outward to both sides rather than allowing it to contact the full underside at once, producing a controlled ride in conditions that would make a flatter hull dangerous. The trade-off is fuel consumption and low speed behavior. A deep V requires significantly more power to climb onto a plane, and at rest, the pointed bottom means the boat rolls noticeably when weight shifts on board. It became the standard shape for offshore sport fishing boats, high-speed patrol craft, and any application where crew comfort in rough water justifies the additional horsepower required. Modified V-hull. The modified V-hull is found beneath the majority of recreational powerboats sold worldwide. It begins at the bow as a relatively sharp V entry, but the dead rise angle reduces progressively toward the stern, flattening to between 10 and 18 degrees at the transom. The forward section handles wave entry reasonably well in moderate conditions, while the flatter aft section provides lift and stability at planing speed, requiring less engine power than a true deep V of equivalent size. The modified V reaches its limit in heavy offshore conditions, where the flatter stern sections begin to pound in a way a true deep V would manage more comfortably. It is the dominant hull shape in recreational boating because most recreational boating happens on lakes, bays, and protected coastal waters, where it performs exactly as needed. Round bottom hull. The round bottom hull moves through the water rather than over it, staying in displacement mode at all times, supported entirely by the volume of water its hull displaces. The curved, continuous surfaces minimize turbulence by eliminating sharp angles, allowing the hull to slip through the water with the least possible frictional resistance at low to moderate speeds. This efficiency made it the foundation of ocean-crossing vessels throughout maritime history, from wooden merchant ships of the age of sail to modern cargo tankers carrying hundreds of thousands of tons across global trade routes. The limitation is roll. Because the curved hull lacks flat surfaces to resist lateral wave energy, it rocks in a pendulum motion that V-shaped hulls dampen more readily. Sailing vessels address this with deep ballasted keels. The round-bottom hull also cannot plane, and attempting to drive one at high speed produces exponentially increasing resistance rather than lift. Cathedral hull. The cathedral hull, also called the tri-hull, produces a cross-section resembling an inverted letter M. A central V hull runs the length of the center line, flanked by 2 smaller V-shaped sponsons that extend outward to the sides. The arrangement traps air and water in the channels between the 3 hulls, generating buoyancy across a very wide surface area and producing initial stability that single hull designs of comparable width cannot match. It also pops onto a plane quickly as the tunnel channels direct air and water pressure under the hull at low throttle. The limitation appears in anything beyond calm water. The wide, flat bow profile that creates stability at rest becomes the source of a punishing ride and chop, with the broad sponsons contacting each wave across a large horizontal surface simultaneously. Cathedral hulls dominated recreational boating for several decades in the mid-20th century before being largely displaced by modified V designs, and they remain in production for fishing and utility applications in sheltered water. Stepped hull. A stepped hull has one or more transverse notches cut across its running surface, creating a staircase pattern toward the stern rather than a single continuous planing surface. Each step allows air to be drawn in from the sides and injected beneath the hull, breaking the suction between water and hull and replacing wetted surface with a layer of air. Water creates significantly more drag than air, and above approximately 30 knots, the reduction in drag produces speed gains of 10 to 15% with no increase in engine power. The performance advantage comes with a handling penalty. The air cushion that reduces drag also reduces grip, and in high-speed turns, the stern can lose its purchase on the water and slide sideways, a condition called transom slide. Stepped hulls require precise throttle and trim management from experienced operators. The design is standard in offshore powerboat racing and increasingly common in high-performance center console fishing boats. Pontoon hull. A pontoon boat has 2 or 3 large aluminum cylinders, typically between 23 and 27 inches in diameter, running the length of the vessel parallel to each other beneath a flat rectangular deck. The cylinders are sealed and air-filled, and their buoyancy supports the entire structure above the waterline. The arrangement produces more usable deck space relative to overall length than any single hull design, because the full rectangular footprint is available as floor space. They're also among the most economical hull types to manufacture. The limitation is seakeeping. The flat underside of the deck has no hydrodynamic shape to manage wave energy, and in large swells, waves can contact the deck directly, a condition called deck slamming that is both uncomfortable and potentially damaging. 3 tube designs, called tritoons, add a center tube that improves planing performance and rough water behavior, though pontoon boats remain fundamentally calm water vessels suited to lakes, rivers, and protected bays. Catamaran. A catamaran divides the vessel's weight between 2 separate narrow hulls connected by a deck spanning the gap between them. Each hull is far narrower relative to its length than a single hull carrying the same total weight would need to be, and the combined drag of the 2 slim hulls is substantially lower than a single hull of equivalent displacement. Performance advantages of 20 to 30% over comparable monohulls are typical. The space between the hulls also means wave energy must simultaneously lift and depress hulls separated by several meters, making catamarans dramatically more stable in ocean swells than monohulls of equivalent length. The vulnerability specific to the catamaran is capsize recovery. A monohull with a ballasted keel has a righting moment that pulls it back upright. A capsized catamaran has no such mechanism, and floating upside down, it is stable in that inverted position. Cruising catamarans manage this through conservative sail plans and sea state awareness. The design traces its origins to the outrigger canoes used by Austronesian peoples to colonize the Pacific Islands. And the same twin-hull geometry now spans applications from 15-foot sailing day sailors to 500-foot high-speed passenger ferries.